So another aspect is in the life sciences field. So we have different interactions at the atom level. It can be atoms interacting within a molecule, within a large protein. It can be subatomic particles that are colliding and interacting between each other, like it's the case at CERN, as I will discuss later. So in science and life sciences, this is also like an aspect we are interested in exploring. But the most common type of networks and analytics and interactions that we encounter on a daily basis is the human networks. So human networks that can result in scientific collaborations, that can result in team sports, as is shown in this figure. Now, the reason I show this figure is the motivation. So in team sports, we have, like in this case, 11 players communicating between each other for a certain task. And we have a graph, and the end goal is to score a goal. Now, of course, now also with the AFCON, we have like different people, including me, sitting in a cafe, watching a game, observing how each player should play, where the ball should go, when they should press, when they should defend. In reality, as you know, like every manager has their own style of play, has their own philosophy, whether when it comes to defending, attacking. And today, it's the job of some data scientists to discern the tactical patterns of these managers. So if we take the frame of, let's say, game 1 to game 15 of FC Barcelona, we can realize some patterns of how they attack when there is a gap in the midfield, when there is a gap in the defense. And if you think about it at a high level, team sports like football, they are a graph problem. It really depends how you see the task. The task can be to create space, to maximize space, to find space, to score a goal. This is the end goal. This is the reward. So now if you go to some postings at their website, you can find data scientist job at Manchester City FC, at Arsenal FC, an AI engineer here, a machine learning scientist there. So it's very common. But now, to talk more about data sets we deal with in, let's say, the academic sense that are more available, now that we know that the graph structures are more common than we think. One example is, as we said, molecular compounds. We deal with that a lot in academia. Another example is social networks, and another example even is traffic networks. So here we can do different kinds of tasks and different, let's say, ways of viewing these tasks. So for example, in the first, let's say, image, we have a molecule with a certain connectivity, with a certain structure, and we have a set of atoms that are connected to each other. One question can be, how can we do, like given this structure of atoms, given this like whole surface, whole compound, can we tell what is the family of this molecule? So this is a graph level classification problem because we are taking the entire surface, the entire compound, and we would like to tell, like, let's say, a label or multiple labels for a whole structure. This is a graph level classification. Another example is, for example, at the node level. Here we have a social network, and perhaps we want something like a recommender system. So we have the central user in the middle that has a certain neighborhood, different types of people that have their own interests, and given her neighboring connections, can we recommend a friend, an activity? This is node level classification because we want to predict the task for one node in this case. And the final example is to see traffic networks as graphs. So in this case, intersections would be nodes, and the highways in between would be the edges. So can we use this data to predict the speed of cars at a daily level, or what should be the speed limit at a certain place? These are different types of problems we can benefit from graph learning. And the problem is that most of people usually are familiar with a certain type of structure that is what we call structured data. That is images and videos, and all of these Sora-based videos that you see, all of the images generated by diffusion models, they are all grid structures containing pixels or with a certain, let's say, arrangement. But this is not the case for a lot of kinds of data that we see, like social networks, telecom networks, biological networks, and the ones I mentioned above. So these are what we call unstructured data, or in more academic term, non-Euclidean data. So how do we learn on these? Because if you think about it, if I take a picture of the Mona Lisa and I shuffle the pixels a bit, this is no longer the Mona Lisa. But if I do the same thing to graphs, I do some permutation of the nodes, I change the way the nodes are spread, it's still the same connectivity. If I don't interfere with the edges, it's still the same graph. It still means the same thing. So how can I transfer the machine learning techniques to graphs? So how do we go from convolutional neural networks to graphs? Well, the answer is with graph neural networks, apparently. So, and today this will be like the main topic I will be discussing. And let's proceed by the simple definition. So obviously, if it's called a graph neural network, then the input data will be, as the name indicates, a graph, a network of a certain topology. So a graph is simply defined by a set of nodes and a set of edges. We have, let's say, in this case, a social network. The people within like the network are the nodes. And then there are certain connectivity, whether it's people, whether it's atoms. We have to define who is connected to who, how well they are connected, how far each node is from each other. So this is where the adjacency matrix comes in. And obviously it would be an n by n matrix, where n is the number of nodes, and it would describe which node is connected to which other nodes. Who are the neighbors? Who are the nodes that are far away from each other? And this adjacency matrix can be either, as in this example, a binary matrix, like two nodes are either fully connected or not connected at all. And it can be a weighted adjacency matrix, like in force fields, like in materials. So you would have then a weight defining the strength of connection, like in chemical bonds, for example. Now, this is for the connectivity. For at the level of each node, we have, let's say, a feature vector. So if you have n nodes, then the feature matrix is defined by n by f. So here there's a like slight mistake. It's a feature matrix, not a feature vector. So if we have n nodes, each one has a vector of dimension f, describing, for example, the height, the age, the I don't know, the activities, the features of each node at the input level. So this will be the data structure that we will use to learn over a graph using graph neural networks. This is the construction phase. And either we are provided with this structure a priori or we have to learn it. So how do we go on learning with graphs? What does it mean to learn over graph using a machine learning model? To make it simple at a high level, let's start with this quote. I'm sure like many of you have heard. يعني قل لي من تعاشر أقول لك من أنت. And this is really the base of understanding how graph neural networks works. It's really like that, because the whole idea is about studying the neighboring nodes, aggregating their features, being biased by these neighboring nodes, and this will already influence the node under question that we are studying. So the whole idea of graph neural networks is based on this concept of what we call message passing. And it's really intuitive. You have a central node that is, in this case, for example, in the image XB in red. It's surrounded by 4 neighboring nodes, each of them connected to it in a directed fashion. And the idea behind message passing is that I want to fuse the features on these nodes towards the central node to update the central node's information. So basically, like a simple way to formulate this is given in the formula on the slide. What this is saying basically is that I am at a certain layer at a certain time step t. And this is the time step of the central node XP. Now, if I want to update it, if I want to say, fuse the information of the neighboring nodes, what do I do? Then the simplest thing to proceed with is to sum the features of the neighboring nodes towards XB, and then do an update function, which can be as simple as a relu function, to regularize the features, to normalize the procedure. Now I have a new representation of the node. Now I have accounted for my surrounding, but in an equal fashion. And when I say equal, this is important, because the way you define the message function m in this equation, this is what defines the type of graph neural networks we are dealing with. because one can say that I want to sum them equally, and this is how a graph convolutional network operates. But sometimes we are unevenly influenced by our surrounding. So in this case, for example, node XA can have more influence on the central node than node XD, for example. So what do you do in this case? This is where attentional convolution comes in. And this is at the base of graph attention networks. This is where we give more attention to some edges connected to like some nodes compared to the other. And this is really like a case-to-case scenario, whether you want to use a graph attention network or a graph convolutional network. So in a graph convolutional network, to recap, all the surroundings are considered equal in their influence. In graph attentional network, we put more emphasis on some nodes compared to some others. And a simple way to visualize how these graph attention network work is the following. There's let's say a PhD student called Adam, and he is the central node. He is the center of attention in this case. So Adam is sleep deprived, and there are many factors that could be associated with the sleep deprivation. Like he did the late night run, he's dehydrated, he's always on the social media, he's doing a PhD, he took a double espresso before sleeping. So all of these are the factors that are like, let's say, that want to form a graph. And once I connect and learn like over different patterns of sleep, then maybe I figure out that this is the reason, these are the main influences on the sleep deprivation, that a double espresso can have more influence on sleep than a late night run or using social media, for example. So this is, let's say, a simple example to visualize, let's say, the importance of graph attention network. Now, the thing is, so far we have given the example of one hop neighborhood. We have accounted for our direct neighbors, the ones I'm exposed to. But let's say I live in Beirut, and I'm always surrounded by people in Beirut. We go to the same coffee shops, to the same restaurants, and etc. But maybe I have, let's say, common interest with someone who is from Tripoli, for example, or from Zahle, or from Sur. These are not directly connected to me as cities, but they are far away. And this is where it's interesting to talk about the notion of multi-hop exploration. So when you have a graph, you don't want to just be biased by your direct neighbors. You want to go for long-range exploration and see what's interesting out there, who has common features with you, who resembles you at a long distance that you don't know about. So traditional GNNs, of course, aggregate information from immediate neighbors, but in many real case scenarios, we want to explore information from long ranges. So in this case, I show you a simple graph where node A is at a distance of 3 from node B. So let's say it's a multi-hop in this case, small still, but it's multi-hop. So how does GNN ensure communication between them? Well, the simple way to think about it is that the layer of GNN, whether it's graph convolutional or graph attentional that we used, we can just repeat it another time and another time until we reach from point A to point B. So one simple answer is to keep adding more layers until K is reached. Because the first time you apply that equation I showed you, you're accounting for your direct neighbor. You apply it a second time, you're accounting for your second hop neighbor, a third time, your third hop neighbor, and so on and so forth, until you reach the kth hop neighbor. So it seems like a perfect and easy solution. Like I can go from A to B by just repeating this process I did, and then problem solved. So, but it's not really like that. It's not that trivial if I want to send the information from A to B. And why is the case? Because graphs and graph neural networks specifically, like humans, they spread information. We spread rumors as humans. We spread talks, but we don't always spread the right information at long distance. And it's the same thing for graph neural networks. When I go also from Beirut to Tripoli, I don't go, let's say, in a straight line unless it's 4 a.m. There's always some traffic in between. And when information flow from A to B, there's also some limitations when it comes to GNNs. There's also some nodes that are in between that are highly densely connected. And this is where like nodes and information collide, and information gets stuck in traffic when traveling from node A to node B. And this is the bottleneck effect that is the main one of the main contributors to the loss of information in graph neural networks. So now we start talking more in detail about the limitations of MPNNs. So this limitation of bottleneck being present in the graphs when information goes from A to B is called oversquashing. It makes sense if you think about it, because as the information travels from point A, in this case, to point B, or point A to point C, the information will be squashed within some specific regions throughout the graph. So at some point, when I make a disturbance at point A, I would want this effect to be felt at B, and I would want the effect to be felt at C. And this is what the Jacobian matrix, if you remember from calculus, does, at least for graphs. So we want the sensitivity of point B with respect to point A to be maximized. We want the sensitivity of point C with respect to point A to be maximized, because this means mathematically that any change in A, that any information flowing in A is felt at B. So this is like why this oversquashing problem is important to deal with. So how do we go around that? Let's recap a bit the limitations, other limitations. So one is the fact that we have oversquashing, as we discussed. One is that it's computationally expensive maybe to repeat the same layers again. And one is similar to like oversquashing, but in this case, it's a bit different. Oversmoothing is when we keep repeating the same information over and over again. When the information travels from A to B, then at some point, the node features will become very homogeneous, and this will result in loss of information, right? So as I told you before, like a graph is defined by the connectivity matrix and the feature matrix. The feature matrix has like, let's say, the descriptions of the nodes. But if I do the message passing operation multiple times, studies have shown that this results in the phenomena of oversmoothing. Now all the features look similar. The model, the classifier, cannot now distinguish point A from point B. So whenever I want to do node level or graph level classification, I will get a terrible performance. So these are the main limitations of MPNNs: to be stuck in traffic, and for everything to become smoothened out. The signal has died, and this is usually measured by what we call the Dirichlet energy. So there are some actual mathematical based measures for this, and the Dirichlet energy will be zero. This is what it means to have oversmoothing, plus the computational cost of repetitive let's say applications of this message passing operation. So now that we know what MPNNs are, what are their limitations, let's talk about some applications of message passing neural networks. So one of them can be found in life sciences. So GNN for protein learning. So this is one project I worked on at the beginning of my PhD. And to clarify, I'm not a biochemist myself. I'm not a protein expert in the, let's say, biological sense. But at the time, I was thinking that I work on long-range dependencies, and I would like to find a real-world application of a system where we have long-range dependencies. So proteins would be a suitable application for this, given that they are large structures that can be seen as graphs, and they do contain long-range dependencies. So in fact, nodes in this case can be the atoms or the residues of the protein, and the edges will be the chemical bonds. So the atoms are spread in 3D space. If I do a k-nearest neighbor approach, I already can get the connectivity of the protein, because maybe it's not defined a priori. And then I have a connected graph that I can feed to a graph neural network. And the task can be, for example, to classify what is the family of this protein, or later on to identify the binding site of this protein. So in simple terms, if you want to design a vaccine, for example, You want to be able to know the dynamics of the ligands binding to the protein and what effect this has. And so if the ligand is considered as a graph, the protein is considered as a graph, then I'm really just studying the dynamics of two graphs together. And this is something where graph neural networks have a high potential in. So how do we go about that? So first we have to remember the challenges that we have long-range dependencies in these proteins, and the regular GNNs do not function well in the presence of long-range dependencies. Why do we have long-range dependencies here? I mean, first, the intuition is that it's a large structure. It is expected that we want to cover large receptive fields to cover the full information. Second, it is known in the domain that sometimes within the protein, there is long distance communications between the residues and the atom that plays a role in the folding of the protein, in the activation of some pathways that scientists try to discern, to analyze, in order to understand the protein dynamics better and the protein function better. So not only they exist, but they are also important to extract for a better understanding of this protein. But first, we want to get a good representation of the protein by covering this whole surface in the embedding space using graph neural networks. But knowing that graph neural networks do not work well with long-range dependencies, how do we solve this problem? Well, the first thing I thought is that if graphs struggle in making two distant nodes communicate, then I should just simply make them communicate. How do I do that? Well, I will change the graph. And this is where we delve into graph rewiring. And the idea of graph rewiring is simply to just change the connectivity of the graph. And this is by either adding edges, removing edges, reweighting edges. So the same analogy can be applied in traffic networks. If I want to go from point A to point B, from Beirut to Juni, by cutting across all the traffic in between, I add an edge, in this case by constructing, for example, a highway, sea-based highway from Beirut to Juni. In this case, an important factor to account for is the fact that it's an expensive operation. But sometimes in graphs, it can be not expensive to just add one or two edges to make two distant nodes communicate. The problem is that how do I add these edges? When do I add these edges? Who should communicate with who? This is the challenge in this case. So we start by doing this knowing that there are some trade-offs, of course. The trade-off is that we are changing the graph connectivity. So sometimes, graphs should be left as they are. If you change something in the structure of the graph, it changes completely the meaning. Yes, this is the main limitation, that we are changing the semantics of the graph sometimes, but this comes at the trade-off of the better information flow across the surface. So it was something I was willing to do, at least as a first try. So how do I use rewiring in this case to reduce the information bottleneck and to improve the information flow? Well, I think of it like this. I have a protein structure, a large protein structures, and then I follow the divide and conquer strategy in this case. So I introduce first a set of agents. And please, in this case today, I will use the word agents many times. So do not confuse it with agentic AI. It has nothing to do with that in that sense. When I say agents, I mean nodes that need to interact with each other. So I start by introducing some agents to cover different surfaces of the protein. So each one is responsible to aggregate information from a certain area of a different color. So we start by the following. We assume that for every large structure, whether it's a protein, whether it's another type of network, we need a combination of local and global information. So in this case, the local information will be accounted for by backbone GNN. It can be a GCN, it can be a GAT, because GNNs, although they suffer from over-squashing, over-smoothing, they can still perform well up until a small receptive field. So I consider that up until a small receptive field, I want to embed the protein clusters with a GCN, for example. Now I do that, and then I want to move now to the global information. I got the local. How do I get the global? Well, I send the information from each cluster towards its corresponding monitor slash agent, which is in this case the virtual node. So I'm moving gradually from local to global by doing a bipartite graph, and now the information flows in one direction from the local clusters towards the global agents. This is step 2. Step 3, I'm now making these agents communicate between each other. And this is like where I get the global fusion of information. Now I consider that all of these agents, 1, 2, 3 up until C, they contain all the global information of the protein in one or a few vectors. And this is very nice because if you think about it now, any two nodes, where however distant they are at the level of the protein, the maximum commute time from point A to point B is 2. So this is the maximum commute time. If they didn't already encounter like at the level of the GNN, then they encountered for sure at the level of the virtual nodes. So once I do that, like this is already like the approach of combining a GNN plus virtual nodes. And this is, you will see in the table in the next few slides. However, I do an extension of this idea. So not only I want to fuse local and global, but I want to rewire the graph based on the information that I got from this combination. How do I do that? Well, here on the level of the edges, if you think about it, I have now attention weights. Why? Because if I use a graph attention network, as I said, from the input protein to the virtual nodes, then I can have some extra scores on the edges, which are called the attention scores. So now I can start pruning the connectivities based on these attention scores. So I can say the edges with the top 20% attention will remain, and then everything else is irrelevant. This is something that I manually set. So then my assumption is that the top contributors from the protein to the virtual nodes with top 20% of attention scores are the ones who are contributing more to the function of the protein. And so therefore, these distant nodes that contributed to high attention scores should be connected to each other. And I will add a few edges in between them. So this result, for example, of between 100 nodes, I have 20 nodes that are very crucial. Instead of fully connecting 100 nodes, which is expensive, I connect only 20 nodes between each other. So I saved a lot of memory cost and computational cost. So this is what I call attention-based rewiring. And all of this that I just described to you is formulated in these equations here. So the first one, in the first equation, I'm just repeating the formula I showed you before. I'm just aggregating the information at the local level. And then I map information from residues to virtual nodes. Let's say like from the different clusters of different colors to the corresponding agents. And finally, I exchange messages between the virtual nodes. This is the GCN plus virtual node approach. An extension of it is the rewiring approach, where I use the attention score at the edge level here to prune the protein graph to select the most important residues and to classify the protein accordingly. This was applied on some peptide datasets, enzyme classification dataset, and binding site identification dataset. So it's a combination of graph level task, like the peptide function, and enzyme classification, and node level task, like binding site identification. Because in binding site identification, you either classify the node as belonging to the binding site or not. So it's a node level task. And these were the results. Like basically, if I use GCN rewire compared to GCN latent, where I get an improvement in the performance, both in like classification setting and regression settings, on the different tasks that I discussed above. And this method performed better than other existing rewiring approaches, where you had to do the rewiring as a pre-processing step. In my case, I do the rewiring in an end-to-end fashion. I don't need to pre-process the graph, which can be expensive, especially, let's say, if it's a very large graph. So this is my first PhD project. It was nice. It was in machine learning for comp bio proceedings, and I would like. I think in the future, one can, for example, adopt a smarter rewiring strategy. I mean, the attention-based one was already good, but maybe we can even more like work by sampling on very large graphs, and then let's say improve the performance even more. So there are various ways one can use these virtual nodes and the rewiring aspect associated with it. And then it was an introduction to using virtual nodes more commonly for different applications. In a separate paper, we did diffusion on these virtual nodes instead of doing a diffusion process on the entire protein, which also saves a lot of cost. And that paper was in NeurIPS of this year. So this is definitely some nice work, but it has its own drawbacks. So rewiring seems to be working well, at least for this case. But in this case, I'm still dealing with graphs that are, okay in size, not too large. They are, let's say, 100 nodes to 1,000 nodes even, which is still a acceptable range. The problem is that if I want to start scaling to very large graphs, 100,000, a million nodes, I would say that in that case, like the rewiring aspect would be much more challenging, and it would be much more difficult to say, look, let's say these two nodes, instead of being now at 5 hops away, they are now at 100 hops away. Can the model still capture them? Potentially, but we'd have to be very lucky with the attention scores that are being learned. So rewiring works well, but in my opinion, for smaller scale graphs, and can still be expensive and a bit stochastic in the selection of the edges to connect. So one question is there an alternative to rewiring for learning long-range dependencies? And what if we preserve the structure of the graph, and instead of learning to change the connectivity, we just learn to spread the information better without rewiring the graph? So this is where I start talking about the other main project we have, which is the revival of spectral GNNs. We'll stop for a bit just in case someone has a question, something. I don't know. But just to take also a sip of water.
Okay, so if anyone has any questions, please feel free to write them in the comments, and we will read them out, or I can read them directly.
This sounds good. Damn. So now we say, okay, we have the, by the way, now you cannot see the screen anymore, or can you still see my slides?
No, we're looking at the meeting.
Okay, now you can see.
Okay, so I have a question before you continue, if you don't mind. It's basically, is it more accurate to say the research is more machine learning based but graph theory aware, or the opposite?
Is it more accurate to say the research is more ML based but graph theory aware, or the opposite? What would the opposite be in this case? And it's more graph theory, let's say, based and less machine learning based مثلا. يعني هو look, it definitely is machine learning based, but it is somehow graph theory aware, but graph theory is more like this in the sense of you want to interpret your graph data. And graph theory is more used when you are given a graph, and you want to, let's say, visualize the distribution of the connection. You want to analyze some metrics of the graph, like the node centrality, for example, like the eigenvector centrality. Like you want, it's the case where you care more about the structure itself, what it says at a static level, less about the dynamics and the interactions within this graph. This is what GNN does. What graph theory is for is more like like telling you like some metrics about the existing graph before you feed it to the GNN. Both can intersect, and this is what I'm getting at in the next part. The intersection of both can be found a bit more in graph signal processing. So this is where we get into more spectral graph theory and how it can be used for the foundation of graph neural networks. So this is what we will talk about just now. Doesn't rewiring change the local global info? How do we go around this if we are changing the whole graph structure? هلا هو rewiring does change the local info. In fact, it depends how you want to aggregate the information. So in this case, I didn't change the local information when I did the backbone message passing. I did it on the graph itself, on the existing structure. The wiring comes more as a bonus. The wiring, what it says is that I have the local information that I collected from the existing structure, and I have the global information that I collected from the fusion of the different parts of the structure. Rewiring is an extra, let's say, benefit where you get a communication between two distant nodes that are far away in the structure. So the final outcome to the classifier will be local information, global information, and distant communication embeddings. The backbone embeddings we got at the beginning, the fused information in the global embedding vector, and the distant communications from A to B that didn't happen at the local level. So we are just like adding these three components together to make sure that now we have a new bridge between A and B that are distant, that are far away, and that that now have to be accounted for within the let's say total embedding. That's why GCN rewire in that slide performed better than GCN plus virtual nodes only. Before, okay, do I answer everything now, Haider, while I continue and we answer later? What do you prefer?
If you want, you can answer these two questions and then we'll stop until you're at the very end.
Okay,
Does that work?
yeah. Before the expensive process of rewiring protein virtual nodes is done, are the tests done for this specific use case to check that it's biologically possible or safe? Um, No, everything. So all of these benchmarks are assessed based on the classification performance and based on the fact that the machine learning model can now better distinguish a certain family of proteins. And this is, as I said, لأنه in this lab, at least we are not fundamentally biologists. The goal of this project is more to show that given a large-scale system, whatever it is, doesn't have to be a biological system, we can improve the information flow and reduce the bottleneck by introducing virtual nodes and by doing an attention-based rewiring. The main goal, or at least it's not at the core of this project to assess the biological plausibility of, like, let's say, if it's a generative model of the proteins, for example, because even AlphaFold 2, 3 do not result in like perfect lab-ready proteins so far. So that's why I insisted that, when I was talking to biologists in ISMB like last year, that this is a use case that can be generalized to other types of networks, not specifically biological networks. So that's GNN. We need to implement some graph theorems, which I find. So Rima is asking, is a GNN can be used for example to find, for example, the shortest path? Yes, Yes, it can. يعني this goes a bit more into the subfield of graph reasoning. So يعني here in graph neural networks in general, what we're trying to do is to get ideal representation of graph structures in latent space. And later the goal is to classify the graph, to classify the nodes and so on. And what you're referring to is an interesting applications that goes to say, okay, can GNNs do what graph theory based stuff cannot do? They can, in the sense of like they can learn over large scale structures, and classify them. But now, can they also like learn about the shortest path from A to B? They can be trained to do that, and I can refer you to some papers actually by a Lebanese guy as well. And it's like a shortest path neural network, for example. And you train the GNN specifically to find the shortest routes. And this goes, there are some people back then in DeepMind working on this, like graph algorithmic reasoning, and so on and so forth. And even like an interesting extension of the thing I presented now goes into learning the graph structure, and not necessarily to find the shortest path, but how can we, given a set of point clouds, generate the ideal structure such that all the nodes communicate between each other. And this goes into a combination of what we call مثلا الكايلي graphs يلي هي an algorithm that generates a structure such that there is a minimal travel distance between any point A and any point B in the graph, either الكايلي graph propagation. But the problem is that it's super expensive to pre-process a set of point clouds as Kylie graphs. Yani as the number of nodes increases, we will suffer a lot with the pre-processing. That's why we need a combination of GNN and graph theory, to be able to do things at scale in a linear fashion. Okay, I will proceed now with the second part اللي هو spectral GNNs. طيب هلا in fact the real motivation behind this second project is a bit of luck. So between these like benchmarks, there was also another benchmark called ChebNet. Now the interesting finding was that ChebNet, when I used it, it outperformed all of the benchmarks you see in this table. When I put virtual nodes on top of it, it didn't matter. When I put rewiring on top of it, it didn't matter. And at some point, it decreased the performance. So I was looking at it, and then I was wondering, what is it with this ChebNet? Why is it performing so well? And then I started experimenting on it with different data sets, and I find that it's still performing very well. So what is ChebNet? So actually, it was done right here in my lab 10 years ago, and it's quite old. I managed to meet the PhD student that did it right when he was graduated, and right when I joined the lab. By then, the paper had already like 17,000 citations, stuff like, I don't know, I don't remember. But imagine, like, he was first year PhD already with 5,000 citations, something like that. So this was one of the first modern graph convolutional networks to be introduced. Later on, followed by like the graph convolutional network message passing of Kipf and Welling. So they were almost in the same time. But here, in this school of thought of spectral GNN goes more into spectral graph theory. Everything we discussed so far about message passing as aggregating information from neighboring nodes, it goes more into what we call spatial message passing, spatial graph neural network يلي هي إنه we just propagate information until everything is covered. But spectral graph neural networks, they account more into some structural, let's say, frequency-based information. لأنه graph signal processing, the goal is to learn in the frequency domain. When the people at LTS2 بال 2016 2017, they tried to make a first connection between machine learning, deep learning, and graph signal processing, which is what the lab originally does. And we are called until now signal processing lab. So this connection was first introduced on GNMs on ChebNet. So what is ChebNet? It's basically based on Chebyshev polynomials, يعني the three equations that you see here, and these are some recurrent terms that have apparently very nice applications. Why? Because if you want to, let's say, analyze a graph in the frequency domain, what would you do? You want to do an eigenvector decomposition, an eigendecomposition of the graph Laplacian. So the graph Laplacian is just the degree matrix minus the adjacency matrix. So it's this simple formula, and it simply tells you about the connectivity of the graph. So it will show some kind of frequencies at nodes that are very highly connected, different frequencies at communities that are much less densely connected. And if you want to analyze the graph, let's say from a, let's say, visual perspective, you do a graph signal processing, you do an eigendecomposition of the Laplacian. The problem is this eigendecomposition is expensive if you have like a very large graph. And imagine having to compute 1,000, 1 million eigenvectors, eigenvalues. It's expensive. So Chebyshev polynomials came in and said, actually, we don't need to fully compute them. We can just approximate them using this Chebyshev recurrence term. And this makes the process much more scalable and efficient. So combining this aspect of the Chebyshev polynomials with graph machine learning, we end up with this model introduced in 2016 that is called ChebNet, Chebyshev Graph Convolutional Networks, where the goal of the neural network is to learn the filters using Chebyshev polynomials, the graph filters, basically. So this is an introduction to ChebNet. And as I said, this was introduced 10 years ago. It was benchmarked on different graph community benchmarks, and it had an average performance. And it wasn't like the greatest performer in a way. So I tested it, and then basically I found that actually this guy is performing super well on even recent benchmarks, because in the GNN community you have always this notion of the old data sets are trash because they do not have long range dependencies. There's new data sets now, like the ones I'm showing you, diameter, SSSP, eccentricity. These have long range dependencies. So no one had ever thought of using this old GNN and benchmarking it on the new data set. Actually, after 2017, people left ChebNet to jump on the GCN because it's easier to understand. It's more intuitive to study message passing rather than spectral graph theory or graph signal processing or شو. So I came back to this notion of ChebNet and I benchmarked it. I found that it has some very, very good results on competitive benchmarks, and even better than graph transformers, even better than newly introduced GNNs. So why was this the case? But no, is it really this perfect no ChebNet? Well, does it have some limitations? And can it solve everything? And it turns out it actually يعني لازم to slow down a bit, because apparently it does have some limitations still, which are the following. And in fact, we did some sort of dynamical system analysis of ChebNet, and it turns out we can perform well up until a certain range, and up until, let's say, K is equal to 3 to 5. What do the figures that I'm showing here mean? They mean these show the spectrum of the Jacobian, the eigenvalues of the Jacobian. So remember the Jacobian matrix that I showed you in earlier slides, and I told you that this is the sensitivity matrix of any node A to any node B. We want to maximize the Jacobian values. The figures that I'm showing you now is for you, those of you who took control theory, they tell us about the stability of the system. And in this case, we want to view the message passing propagation in multiple hops when going from 1 to 10 مثلا, as an information flow as a dynamical system. What can dynamical systems be described as? As differential equations. How do we represent the stability of a dynamical system that is characterized by a certain differential equation. And we study the eigenvalue distribution, in this case of the Jacobian. The circle that you see in these figures is called the stability region. So whenever the eigenvalue starts spreading outside the stability region, we know that the system has exploded and the information propagation is no longer stable. So a good analogy to think of this is the following. It's to say that information flow is like heat transfer. In the ChEPNet case, it's more similar to dissipative diffusion. And it can cover a certain receptive field. In this figure, it's not very fair. And it should cover at least 3, 4 hops, 5 hops before it loses the heat, before it starts not being able to retain the heat. While non-dissipative propagation, ideally, we want something like that to retain the heat while going from A to B across a large number of hops. So how do we, like, let's say, transfer this analogy of heat transfer من like graphs, like from a heat transfer perspective to an information flow perspective. يعني in this case, instead of retaining the heat, we want to retain the information flow, which again is described as a dynamical system. طب هون انا قلت انه we have ChEPNet, we have its performance, its benchmark performance, we have its stability analysis. يعني we know that as if we treated ChEPNet as a dynamical system where information propagates from A to B, like the system becomes unstable. But then how do we make it stable? And then comes the novel contribution that we have. It's called stable ChEPNet. And we cast ChEPNet, as I said, as a continuous time ordinary differential equation. Well, now the goal is to preserve the information flow while going from A to B at a level of k steps. Well, to do that, we should we enforce some trick called the anti-symmetry trick. What this does basically is it preserves the information flow and then it results in the eigenvalue distribution being stable. As you can see here in the figure, now the eigenvalue distribution goes from an unstable distribution to a distribution that is fixed across the imaginary axis. With this stable ChEPNet, when I tested it on, let's say, the barbell task, it was the one that remained the most active, the most, let's say, okay, perfect. لأنه in this case, the goal was to, by the way, I apologize, there was a missing slide here that I think it was hidden or deleted by mistake. Anyway, if you go to the original work, basically stable ChEPNet beat ChEPNet at all the benchmarks of protein classification, of enzyme classification. In this case, the barbell task is basically you have two different clusters of nodes, and there is a thin bridge in between. The goal is to transfer information from one cluster to the other without losing the information. So even ChEPNet, يعني بكل عظمته, at some point it was losing the information when the number of nodes was 50 per cluster. So I have 50 in cluster A, 50 in cluster B, and thin bridges in between. ChEPNet at some point failed. Stable ChEPNet is the only one that survived because we put on it this condition of anti-symmetry of weight preservation that resulted in this perfect alignment of the eigenvalue distribution. And this work got a spotlight at NeurIPS, so top 3% of submissions this year. So the community thankfully liked this work, and then we aim to spread it around to for people to use it in more practical settings and protein learning and so on and so forth. So this is the second project I wanted to discuss today. And then given time, it's been almost an hour, I wanted to do something like this. I can quickly cover the last part, which is the GNN for particle physics. And if you want, you can write some questions in the chat, and I will try to answer them along the way. So one thing I did and this is during my master's. I will skim through the slides. Like if you don't know, the compact muon solenoid is basically the CERN detector to detect the particle collisions. And then basically, let's say we start aggregating information from different layers. It's like an onion layers that collect different information about particles traversing throughout them. So we deal with too much data. We need to, let's say, save some, let's say, computational power with regards to Monte Carlo simulations, for example, and so on and so forth. So people at CERN also decided to use AI, GNN application with particle physics. It's basically to take these particle jets and particle collisions and model them as graphs, and the fact that now we have a shower of particles, and these particles will be the nodes, and the KNN connection of these particles would make the whole thing a network structure. Now I have a GNN that can learn over particle jets at CERN at different layers. At the level of all of these layers that you saw here, we have a GNN learning over each layer and then across the layers. So the way I did it is I have an input array. I remove the empty cells of the detector, and I take the ones that have a noise, or I mean that has a signal. Sorry, and then I perform a message passing process until I map them to a latent space, and then until I'm able to sample from this latent space and then generate a particle jet that can be this like model called Falcon can be used for particle physics simulations and so on. And these are like a comparison between original jet and deconstruction jet. And again, this was in 2020, so and I apologize for the resolution. Future potentials of GNNs. Now they are in high demand in material science, in biological networks. As I said, there are different applications of GNNs. Everything that can be modeled as a graph, material structures, you have also the lattice structures that you can see as a mesh. In telecommunication networks, now GNNs are accelerating as well. And then, as I said, there are the limitations of long-range dependencies that we can tackle either through rewiring or through better information propagation. And it's really like a selection problem, depending on the size of the graphs that we are dealing with, and the type of task that we are trying to solve. فإنه إذا you're interested in rewiring and graph information propagation in general, don't hesitate to reach out. I'm happy to talk more about GNNs at any time. I thank Haider and the team for organizing this presentation.
Thank you, Ali, for this wonderful talk. It was very, very, very informative and very nice to hear, given your experience in the domain. And we can immediately start with the question. So Wad is asking, what would a good learning roadmap for GNNs look like for someone with basic machine learning knowledge?
Is this written? Ma, I cannot see it. Can you repeat the question? لأن ماني قادر على الشات ما في شيء
I
جديد.
see. So it's what would a good learning roadmap for GNNs look like for someone with basic machine learning knowledge?
إيه لا ليك هو look any machine learning project would require you to at least play around with the tools. So in my case, I've been working with GNNs for like almost 6 years now, and I've seen the libraries evolve. I've seen I've worked with first Keras, then PyTorch, then it became easier. Then PyTorch Geometric came out, and now everything can be done with vibe coding with ChatGPT for basic stuff. It's really good. So I think look, there are of course some very good online tutorials. It really depends the time you want to allocate to this. In my opinion, if we go to PyTorch Geometric website alone, it has some very informative Colab notebooks that you can load and play around with. The first step is just play around, just have fun, like visualizing graphs, creating graphs, learning the language of constructing graphs. لانه يعني you should be able to understand مثلا انه a sparse graph structure, how it's represented, what's a good way to represent a graph, how do I construct a graph, is it given to me a priori or not. PyTorch geometric is an excellent starting point, and it's the main reference for like coding in the graph community. And then, of course, يعني once you know how to construct a graph in PyTorch, in Python, in PyTorch Geometric, if you know already how to implement any machine learning layer, whether it's a transformer, then you can easily transfer that to apply everything that I mentioned. Graph Attention Network, إذا بتفوتوا على البايتورش Geometric website في get.conf function with examples, with everything. Once you play around with these, you start understanding how things work. And of course, in parallel, you should be able to to find time to read blogs about graph attention, graph convolution. And it's always the first intuitions on the equations that I showed you. The equation I showed you at the beginning, ideal message passing equation. If you understand that, it's easy to generalize to all other equations. يعني شو بتزيد عليها بعدين attention score بتصير graph attention. بتزيد عليها شيء LSTM بتصير temporal GNN. بعدين there are variants of this equation. Even يعني my model, it's a variant of Chebnet. But we are always doing the same thing. We are always updating the node information. But the thing is, how do you want to update them? On what are your assumptions? What is the inductive bias? يعني I would say يعني to هيك يعني to summarize it, the code work يعني in PyTorch geometric is important, and to go through the Colab notebooks. But in parallel, even if you're not a researcher, there are some like benchmark papers يعني that introduce you to GNNs. يعني reading more and more papers about GNNs and their variations, review papers on GNNs is always helpful. لأنه doesn't يعني it's not enough بس إنه you just understand the code and play around with it. It's also nice to have the intuition. And sometimes it's simpler than you think. And I know I work until now with people who are more in biology. They have never like worked with GNNs. They barely know what GNN is. But once they get this intuition of like, we can actually take your system, which is a protein or a gene interaction network. Once you know what is the perfect connectivity in that network, then the rest is easy. And the rest, us the GNN people can do. And the challenging thing is to say, does this graph structure make sense? Does this message passing framework make sense? Do we have long-range dependencies? How, if so, how do we deal with them? Is it a very large graph? If so, can we apply graph transformer? Is that too expensive? Can we do it differently? And all these questions go into the roadmap إذا بدكم. فايه ما بعرف اذا حدا كتب شيء جديد central by Google Research potential yes external website a gentle introduction to graph. ايه يعني there is many things like this link that Marwa sent يعني في كمان geometric deep learning books وعدة. بس انه I'm not يعني I'm not reading any books on GNNs لانه at some point you read in between masters and PhD you read hundreds of papers literally, so يعني everything is already in your mind. But I would say يعني these blogs on medium.com, blogs like that, they give you nice visuals, they give you a nice intuition. بعدين if it really depends, if you are just a life science practitioner, it's enough to apply a GNN as it is. You don't have to go through all the math. يعني بس إنه if you're someone who wants to improve on GNNs, then it gets messy. يعني now already the field is a bit like مش saturated, but it's getting هيك more and more competitive to come up with very scalable GNNs. And now I think the representation learning part and long range dependency and stuff like that, we agree to disagree in whether we use graph transformers or مثلا شيء مثل stable Chebnet, stable propagation. Now the next challenge will be how do we scale them? لأنه for now transformers are still the hot take لأنه they can be scaled and parallelized on multiple GPUs. Graph neural networks can be more like it's more challenging to scale them. يعني once one is able to do that, then we can have graph neural networks that are scalable at a lower memory cost than transformers. And if you think about it, transformers اللي هن at the core of everything around us, chat GPT وكل شيء هن transformers, they are graph networks. But instead of connecting a few components together, they connect everything to everything. This is what a transformer is. It's a fully connected graph. A more simple way, but it's not completely true, is that a fully connected graph attention network. It's super يعني it requires a lot of memory and time, but at the same time it's parallelizable. That's why it's being used. فإذا one can come up with an argument that we can parallelize GNNs at the same efficiency, then it's more like elegant and it's cheaper. So yeah, ما بعرف إذا حدا عنده question. على كل حال يعني my email is like in public. If you just search on the PFL database, you can always reach out if you have questions about GNNs, about rewiring, graph learning, ChipNet, whichever.
Perfect. With that said, thank you once again, Ali, for this wonderful talk.
Thank you.
And definitely, if anyone has any questions, feel free to reach out. Ali is definitely your guy to answer any inquiry that you have and the best source that you can have on this topic. And many thanks for making this happen. And have a nice evening.
Have a nice evening. Bye bye. Bye bye.